All right, guys, so we are going to be moving in here to part 2 of 3.1. We're going to talk about some transformations that can change the sine and cosine graph. The first 3 we're going to be looking at are the amplitude change, the reflection over the x-axis, and a period change or a cycle wavelength change. The next part, part 3, will go over vertical shifts and horizontal shifts. All right, so amplitude, first one. This one is actually pretty easy. So the amplitude is sort of the height of our wave or our curve here. So the distance from the midline to a maximum, or the distance from a midline to a minimum. That's the amplitude. So in our standard curve, our standard sine and cosine curves will have an amplitude of 1. But if we want to change that, right here, we just multiply by a constant. Remember, that's the same way we stretch pretty much all functions, right? If we want to take a function f of x and we want to do a vertical stretch, which is what an amplitude change is, we multiply that by a constant. Now, stretching it, we multiply by something that is greater than 1. That'll make it taller. That'll make it have a higher amplitude. If we want to compress it down, we're going to multiply by something between 0 and 1, right? So a fraction like a half or a third or even a decimal of some sort, but we're multiplying by a constant to our function. That is for sine. It works the same for cosine. So it would just be a times cosine of x. That a value, whatever it is going to be the amplitude. So if we have a 2 in front, that means we're going to have an amplitude of 2 instead of 1. If we have a 3/4, we'll have an amplitude of 3/4. So instead of going up to 1 and down to -1, we'll go up to 3/4, down to -3/4, and so on. Again, this one's pretty easy, pretty simple. The amplitude is always the, actually technically always the absolute value of this number in front of our function, because a could be negative, right? There's no reason we couldn't do like -3 times sine of x. We couldn't do an equation like this. Well, 3 is the amplitude. It's the absolute value of that number. The negative is a different transformation. The negative is a reflection over the x-axis. I will say also just over the midline. Now, technically for our base function, it will be over the x-axis, but if we start shifting our graph up and down, it's actually going to reflect over the midline instead. That just sort of has to do with the order that the transformations apply. I mean, technically it's reflecting over the x-axis and then moving up or down. We'll get into that later. That's not so important, but we will do reflections, and pretty simple, right? So all that happens is instead of this being a maximum point, it reflects down, and it's a minimum point now when we have a negative in front. Instead of this one being a minimum, it reflects up to be a maximum. And so we end up getting a curve that's just sort of a mirror image of what we have if there's a reflection. All right, we'll throw in reflections here and there just to keep ourselves on our toes. Okay, so let's graph. Let me make sure I didn't go 2 slides. Yeah, only 1. We're going to graph y equals 2 times the sine of x. So we are graphing a pretty basic sine curve where the only change is this 2. So our amplitude is going to be 2. That just means instead of going up to 1, we are going to be going up to 2. And instead of going down to 1, we're going to be going down to -2. As we get sort of more and more complicated graphs, we may want to include some more sort of lines and things on here, but our midline for this problem is going to be the x-axis because we didn't shift it up or down at all. Our graph is going to be hitting its maximum here at 2, and it's going to be hitting its minimums down here at -2. So everything's going to be happening in between these values. I may draw these lines on graphs, I may not, doesn't really matter. So we're graphing sine with still a period or a cycle of 2 pi. There's nothing in here. We haven't really talked about how to change it, but there's nothing in this equation that would change our period. So we're graphing sine. So I'm going to go back to the 5 friends for sine. We graph a midline value at 0 at the start of our cycle. and at the end of our cycle. So 0 is the start, 2 pi is the end, and in the middle, in the exact middle of our cycle, which would be pi. So these are the 3 midline values for a sine graph. Those are the first, third, and fifth points of our 5 friends, right? And then at the 1/4, so this is 1/4, right? If we kind of chunk this out, this is 1/4. This would be, now we're hitting half of our cycle. And then this is 3/4 of the cycle. And this would be 1, the whole cycle. That's what I'm talking about when I say these quarter points. Anyway, at the 1/4 point, we are going to be at our maximum, which is going to be 2, because we have an amplitude of 2. Remember, usually it's down here at 1, but we're stretching our graph up. We're changing that amplitude, so it's up at 2. And then at the 3/4 point, we're going to be down at our minimum, which is -2 again, because we're stretching it down with that amplitude shift. And those are our 5 friends. So we have our first, second, third, fourth, and fifth points of our 5 friends, and then we just kind of sketch out the curve. And this one's going to be tricky for me to sketch. I'm going to do my best, but here's a sine curve. There we go. One cycle of our sine curve from 0 to 2 pi. Using that 5 friends or 5 points method. Let's go ahead and clear this, and we will look at another one. Oh, my fault, sorry. We're going to look at a few graphs of sine. So here, just instead of graphing a bunch of these, let's just look at some examples. So the blue equation and the blue graph here, this is our basic sine curve. Let's just focus in on one cycle. So I'm going to go from 0 to 2 pi, which is right here. Inside that box, this is a single cycle of all of our graphs. So the blue one is our basic sine curve with an amplitude of 1, right? You can see it goes up to 1, and it goes down here to -1, right? We can see that as well. And as we look at the different equations, we can see the amplitude changes and how it causes the graph to go higher and lower around our midline. So second one has an amplitude of 2. That's the orange one here. It goes up to 2 and down to -2. But the points that are not affected at all are these 0 values, these ones that are actually on the axis or on the midline. Those stay the same. Let's keep going looking through these. The third one here is this sort of green or teal colored one. Has an amplitude of 3. So again, we're going up to 3, going down to -3. And then the last one that's shown here is an amplitude of 4. So up to 4 and down to -4. We can have any amplitude we want. These are whole numbers, and they're not even that big. We could have way bigger amplitudes if we want. We could have an amplitude of 100 or 1,000,000 or whatever. I mean, those could exist. They would be pretty obnoxious to draw, but we could do it. We can also have amplitudes that are not whole numbers, so fractional values. We could have amplitudes that are even smaller than 1. Yeah, so we could have like sine of, 1/3 sine x. That would give us an amplitude of 1/3. So instead of going up to 1, our amplitude would be here at 1/3, which is pretty low. It would be going up to 1/3 and down to a -3. So if I could sort of sketch that, it would be something like that, right? Much smaller amplitude. Could also have amplitudes that were, improper fractions. So we could have something between 3 and 2. So like 9/4 sine x. Right, 9/4 is like just a little bit bigger than 2. So we'd be going a little bit more there. So going just a little bit past 2, a little bit down. So our amplitude can be anything we want. Fractions, decimals, whole numbers, whatever. Those are all positive. Obviously, if any of them were negative, we would just be taking everything and we'd be flipping it over the midline, flipping it over that x-axis in this case. All right, let's go ahead and examine a smaller one and a cosine graph. So that's cool. Still going to have a period of 2 pi, so that's why I have this default scaling here for us. We don't need to even draw it out. Amplitude here is 1/4. So that is going to affect my scaling of my y-axis. So let's just put this to be 1 and -1. Obviously, we could kind of create whatever scaling we want. We could just make an arbitrary point here and call it 1/4 and then scale it down there. But I'm just going to try to make this sort of reflect that this is a pretty squashed down curve. So 1/4, this would be 1/2, right? Halfway, and this would be negative 1/2. Here would be negative 1/4, and here would be negative 3/4. We don't need to be this, maybe this precise, but I'm going to do it for this example just to show what's going on here. So here's our scaling. We're counting up on the x-axis, or sorry, up on the y-axis and down on the y-axis by 1/4 increments, 1/4 of a unit. And we have our scaling on the x-axis. It's a standard 2 pi period, so we're going to go from 0 to 2 pi. There's nothing in here that's going to affect the period. Again, we'll talk about that in the next section here, but nothing here that changes that. So let's just go ahead and graph our cosine curve. So our 5 friends, cosine is at its maximum at the beginning of our cycle. It's back up at the maximum again at the end of the cycle, which is at 1/4. Remember, that's our amplitude. And at the middle of our cycle, at pi, it is down at its minimum. So there's our first, our third, and our 5th points of those 5 friends for cosine, keeping in mind we're doing cosine. And then at the 1/4 and 3/4 points, cosine is at its equilibrium or at its midline. So there are our 1, 2, 3, 4, 5 points that make up our 5 friends. And here is cosine. So sketch that through. Looks like when it's narrower like this, I have a little easier time sketching it. But anyway, that's a good cosine curve with an amplitude of 1/4. Okay, let's keep moving forward. All right, so one more. Here we have a cosine curve with an amplitude of 3. Amplitude is 3, but then there's also a reflection. Okay, so let's do both of these things. So the amplitude means that I need to scale my axis to go up to 3 and down to -3. -3. Cool, so it's going to be a very up and down curve here, lots of movement vertically. And also there's a reflection, so that's going to be important. Any of our minimum values are going to reflect up to be maximum values, and any of our maximum values are going to reflect down to be minimum values. So let's go ahead and see what's going on with that. So we want to start by graphing our 5 friends. We still have a period of 2 pi, so we're not affecting that at all. There's no number in here that would change our period, so 0 to 2 pi, have it out scaled for us. Now, usually cosine starts up at its maximum and ends at its maximum, but these points are not what we're going to be using because we have a reflection. That negative is a reflection. So instead of starting at its maximum, we are going to be starting at the minimum and ending at the minimum. And instead of being at a minimum for our midpoint, our middle point here, the 3rd point, we're actually going to be up at the maximum. So I'm going to graph that point as well. So I'm going to erase these that I kind of used there to help me. And then the points that are actually unaffected are the ones that are on the midline, right? If we're reflecting across this midline or across this x-axis, since those points are on the line of reflection, they don't move at all. So here is our reflected 5 friends, and we sketch in the curve. So let me see if I can do this. Ooh. This is pretty bad. I think you guys get the point though. So I don't really need to make this work of art. There we go. So pretty hideous cosine curve. Hopefully you can do a little better on yours. I find it hard to draw it on this for some reason, but there's our cosine curve. It is reflected. It's kind of upside down from what we're used to seeing. And it has an amplitude of 3. There we go. All right. Now, here we go. We have the third transformation. We kind of sneakily talked about the first 2 together. Talked about amplitude change and reflections in that same one there. But now we're going to talk about the period change. And this is certainly one that is tricky. So obviously the period that we're used to looking at is from 0 to 2 pi. That represents a full rotation around the unit circle. So our graph performs one cycle from 0 to 2 pi. And then it keeps repeating because we just keep going back around and around that circle. Well, we can change that. We can cause the period or the cycles to come faster, to be less than 2 pi, or we can extend them out so that it takes longer for it to complete a full cycle. And we do that by multiplying the input variable, the angle, right? Remember, x is representing an angle. We multiply that angle by a constant. Now, if we multiply the angle by something greater than 1, that is going to shorten the cycle, okay? The way that I like to think about this is if I multiply it by a number greater than 1, let's just say 2. So we'll say we multiply by 2. That means when I put an angle in for x, I'm actually taking the sine of an angle that's twice that big. So if I put in, pi over 3, I'm actually going to multiply that by 2 and take the sine of 2 pi over 3. So things are happening a little faster, twice as fast. We're moving around that circle because every angle we put in, we're actually taking the sine of a twice that measurement. So by putting in a number that's bigger than 1, we are increasing the speed with which we are sort of moving around our unit circle, causing the graph to oscillate up and down faster. Whereas if we put something that is in between 0 and 1, we're actually sort of decreasing that speed. Let's just say we have a 1/3, for instance. So for instance, if we plug in an angle of pi here, we're actually doing 1/3 pi. We would actually be calculating the cosine of 1/3. So we're moving now around that unit circle a little slower, 1/3 of the speed, which causes it to take longer to make a full cycle. If we're moving slower around the circle, it's going to take longer. Anyway, let's summarize that here. So if b is greater than 1, we are going to shorten the cycle, or the period. That's not how you spell cycle, but that's okay. Cycle. The period is going to be smaller. We're going to decrease the period. And if b is between 0 and 1, we are going to lengthen the cycle. It's going to take longer to do a full cycle, longer than 2 pi. All of this is relative to 2 pi. And we actually have a nice formula here that kind of tells us the exact relationship. So whatever our b value is, whatever we are multiplying the angle by, the x by, we can calculate how that directly affects our period or our cycle length by doing this formula. Period equals 2 pi over b. And we'll make use of that quite a bit. All right, so let's go ahead and look at two sort of graphs here. We have our basic cosine curve, which is the blue one. So blue is cosine. Start at our maximum, right? I'm kind of marking out the 5 friends just to make sure we see it. Start at maximum, end at maximum, minimum in the middle, and then our midline points. So that's our 5 friends. We can see that's our basic cosine curve. And it has a period of 2 pi. It starts at 0, ends at 2 pi. It does one cycle in that time. Right, this is one cycle, right here to here. One cycle, or period. Okay, from there, we want to look at the other graph, the green one. The green one, if we kind of follow it along, it's at its maximum here, and then it's back down to here. It's at its midline, and then minimum, and then midline, and then maximum. So here is a cycle. Here is one cycle of this graph, or one period of this graph. But we're just doing it again. We're doing it the whole thing over. Oh, and this one. We're doing the whole thing over again. Here, right here is another cycle. That's a second cycle. So in the length of 2 pi, this graph is actually creating 2 full cycles. There's kind of 2 ways we can think about it. One, we can think about what is the actual length of one cycle for this green graph, which is another way to say what's the period, right? Well, the length of that period, we're going from 0 to pi. That's where that one period is. I'm going to outline it in green so that hopefully we can see it. 0 to pi, 0 to pi. That's one cycle right there. So that's one way to think about it. The period is pi, or the cycle length is pi. We can also calculate it. Remember that formula from the last page said that the period equals 2 pi divided by b. b is 2. 2 pi over 2. Twos cancel. We end up with a period of pi. So we can kind of look at it either way. We see it on the graph. We see it in the formula too. It has a period length of pi. It takes that long for it to do its full cycle. The other way we can think about it is how many cycles existed in that usual, that typical default 2 pi interval. So let's kind of examine that. 0 to 2 pi, that's here to here, right? 0 to 2 pi. There's 1 cycle, 2 cycles. 2 cycles, that's the number. That's the number that was in there. There's always going to be b cycles in 2 pi. So whatever that number is, whatever that number there, we say b, which is 2. In this case, there's 2 cycles in 2 pi. There's always going to be b cycles there. Some people call this the frequency of the graph. This is more of a physics term, but the frequency of the graph. How frequently is it oscillating in this kind of standard interval? Let's clear that out. We'll look at another example here where we do something different to the cycle. All right, so here we have a, I think I mixed these up, my fault. So the black graph is actually this one, and the red graph is this one. So sorry about that. Let's fix that. So our standard sine curve starts at midline, ends at midline, and in the middle. So that's 2 pi. That's our standard period length. And obviously the maximum and minimum points that we get with that as well. That's our basic sine curve. What we have here with this equation, sine of 1/2 x, is we've lengthened that period, right? Notice how we start at equilibrium or midline, we end at midline, in the middle, we've lengthened it. It's like twice as long now. So again, we can think about this 2 ways. We can think about this, what is the period of this black graph? And we can see that it's 4 pi. It goes from 0 to 4 pi to complete 1 cycle. Or we could come up with that formula, right? Period equals 2 pi over b, which in this case, our period would be 2 pi divided by 1/2. Dividing by 1/2 is actually multiplying by 2. Get the same value there, right? We can see it on the graph, or we can see it in this formula. Again, the other way to think about this is how many cycles does it complete in a standard 2 pi? Well, in 2 pi, it doesn't even complete a full cycle. It only does a 1/2 cycle, which is b, right? B cycles in 2 pi. So there's 1/2 of a cycle in 2 pi here. All right. I'm going to go. All right, so we're going to be looking at some equations of sine and cosine, and we're going to try to just identify the period of these particular equations, these particular graphs. So to do that, obviously, we need to remember our formula for that. It's 2 pi divided by b. B being the multiplier that is in front of the x, the input variable for our trig function. So I'm kind of underlining them, are the b values. So our first one, we have a b is 2, so pretty simple. 2 pi divided by 2. So we get a period of pi. So when we have a period that is different than our standard 2 pi, we really need to think about how that is going to cause the scaling of our x-axis to be different, right? We're not going to be going all the way out to 2 pi anymore. We're only going to be going out to pi. Our graph is going to complete 1 full cycle between 0 and pi. And then we need to break this down into fourths. So halfway in between there, right, we would have pi over 2. And then halfway in between 0 and pi, we have pi over 4, 1/4 of my period. And then here we have 3 pi over 4, or 3/4 of my period. And that is what we would be using to graph this 0 to 2 pi, this particular function over here. I'm going to go ahead and delete that. Second one, we have sine of 1/4 x, so our b value here is 1/4. So quick calculation here, 2 pi divided by 1/4. That's really 2 pi times 4. So we actually get a period of 8 pi. So in this case, our period is much larger than normal, 4 times larger than normal. So when we go to graph this again, I'm going to just do this for a few of them. we're going to need to scale our axis appropriately. So we're going to be going all the way out to 8 pi, you know, from 0 to 8 pi. And in the middle here is 4 pi. 1/4 of my period would be 2 pi and 6 pi. So we want to break this up into these 4 intervals still. Just now we're going all the way out to what would be the end of our period now at 8 pi. All right. Next one, we have a b value, a little bit of a different one, a b value of pi. Well, let's see kind of what that looks like. Period is 2 pi divided by pi. Well, that just means my period is 2. 2 is a number, just like 8 pi is a number, so we could have a period of 2 if we want. Again, just real quick, what's the scaling look like for that? Right now we need to go, instead of from 0 to 2 pi or 0 to pi or 0 to 8 pi, we're going 0 to 2. That's smaller than pi. That's actually the smallest period that we have on here so far. Halfway in between that would be 1. Here we would have 1/2 between 1 and 0, and then 3/2 between 1 and 2. Sometimes it may be hard to find these quarter values, particularly if we end up with sort of a strange period, which we may in some of these problems. So finding these quarter values can be tricky. All right, let's just go ahead and buzz through the rest of these. So next one, we have a b value of 4. So p equals 2 pi over 4, which is equivalent to pi over 2. So that's a short period. Again, we would want to scale our axis appropriately. Here would be a strange one when I do this one, because when I do this, 2 pi divided by b, which is 7, that doesn't even simplify. I'm literally getting a period of 2 pi over 7. That is going to be a pretty strange period to actually scale on our axis. So just kind of illustrate this as being a bit of an oddball. 2 pi over 7. We're going from 0 to 2 pi over 7. Thankfully, we're starting at 0 here, because we can also have horizontal shifts that really mess with this even further, which we'll see in the next section. So 2/7 pi, halfway between that, it's going to be 1/7 of pi. But then what are these quarter values, right? Well, we have to think about it, right? Between 0 and 1/7, there's actually a couple different ways that we could go about finding this. I'm gonna give myself a little bit of space up here. I could average those numbers. So I could take these two values here. Oops. I could take, what am I doing? Okay. I could take 1/7 pi and 0, and I could literally just average them. 0 plus 1/7 pi, and average those. Well, adding 0 doesn't do anything. Dividing by 2 here is going to turn this into 1/14 pi. 1/14 pi, that's a pretty messy number, not something that we're super thrilled about. So this is 1/14, 2/14, 3/14. That does sort of help us a little bit, though, to figure out that particular value. Again, the scaling can get pretty messy especially when we have kind of strange period lengths or strange cycle lengths that are not very standard. All right, and then the very last one here, we have pi over 8 as our b value. So period equals 2 pi divided by b, which is pi over 8. Okay. Dividing by this, let's just turn this into multiplying by reciprocal. So 2 pi times 8 over pi. Pi's cancel. We're going to get 16 here, 16. So a period of 16, that's actually not one that's too hard to scale, right? 0 to 16, 8 would be in the middle, 4 would be our quarter point, and 12 would be our other 3/4 point. That one's actually not too hard to scale. When we end up with these kind of nice whole number period lengths, actually I think it's probably going to be even easier for you than kind of more standard things like pi or even pi over 2, because dividing this is a lot easier. All right. So let's go ahead and put together all of the different transformations that we've talked about today. We're going to have actually all 3 of them present in this particular one. So we've got, first thing I notice about it, we've got a reflection. So we are going to be reflecting. I'm going to just write these down, reflection. That's what the negative is. We have a amplitude of 4, remember. So amplitude can equal 4. And then this b value is going to change our period length. It's going to stretch it out, right? So we have period equals 2 pi divided by 1/2, which is 4 pi. So instead of going from 0 to 2 pi, we're going to go from 0 to 4 pi. Again, I know that I'm starting at 0 because this is a standard sine curve. There's no horizontal shift taking place. We haven't talked about that yet, so I'm glad that it's not present on this problem. Okay, there are a few different places that we could start. I'm going to start with the scaling of my x-axis because that kind of goes well with what we were talking about on the last slide. So we are going to be going from 0 out to 4 pi, and I'll just make use of the entire space. I haven't been saying that, but I've just been trying to make use of the entire space of my axis just to spread things out nicely. So we're going from 0 to 4 pi. That's going to be 1 cycle. Halfway in between that is 2 pi. That's halfway between there. Halfway between here is going to be pi and 3 pi. So we get our quarter points there, 1/4 and 3/4 points with those. The next thing that I need to do is I also have to scale my y-axis. And remember, that's kind of based on my amplitude here. So a standard sine curve would only go up to 1 and down to -1, but we're going to go higher than that and lower than that here. We're going to go up to 4. So 1, 2, 3, 4. I'll mark that as 4, and I'll try to scale that evenly down here. 1, 2, 3, -4 here. So we're going to be going up to 4 and down to -4 as we sort of oscillate. All right. The only other thing to take into consideration here before I just start graphing all my points is the reflection. Don't forget the reflection. That's a common thing that people do. Remember, our kind of standard sine curve has the 5 friend points here, beginning, middle, end, and then it goes up first, middle there. So down in the middle of that. So kind of looks something like this. We are reflecting. So we're going to be reflecting across our midline, across the x-axis here. So this point here, which is up, is going to have to go down there. And this one here is going to have to go up there. The points that are present on our midline aren't going to be moving. So what we should end up with is a reflected graph. And something like this. So this is what we're going to be working with. So keep in mind, anytime you have that reflection present, before you start plotting all of your 5 points there, think about the reflection and how that's going to change things, right? Any maximum points will become minimum points, and any minimum points will become maximum points so that they kind of flip. All right, let's go ahead and graph it now. The 5 points, that is. So sine starts at its midline, ends at its midline. In the middle, it's at its midline. Remember, we're not going to the maximum first. Sorry. We're going down to the minimum first. The minimum is all the way down at -4. And then we're going up to our maximum here at this 3/4 point, all the way up at +4. Take a look at it before you draw on your line. Just make sure you've accounted for everything, okay? We got our reflection. We went down and then up. So that's the reflected sine curve. So we have that taken care of. Our amplitude is 4. We did go down to -4 and up to +4. And we have a period of 4 pi. We're going from 0 to 4 pi. Just double check that you did all those things before you jump straight in. And then I will try to sketch this curve out. And it should look something like this. So reflected sine curve, 1 cycle of it. That's all we really need to graph. All right, I'm going to go ahead and clear this off. And this will be the last one that I look at today, for part 2 rather. So let's make a list of all the things that we notice here that are going on. First thing is there's no reflection, there's no negative here, but there is an amplitude. So we have an amplitude of 1/3. That means that we're going to be going up to 1/3 and down to 1/3. We're not going to be going up to 1 and down to 1. It's going to be a little more compressed. We also have a b value here, this multiplier in front of our x variable. That's going to affect our period. So let's take our period. We do 2 pi divided by b, which was pi. So our period is going to be 2. We're going to go from 0 to 2. Again, I know I'm starting at 0 this time because there's no horizontal shift. We haven't talked about that yet, but that's something we need to think about in the future. We only start at 0 as long as there's no shift left or right. But we're good, 0. And we're going to go to 2. Doesn't matter. I'm going to, again, make use of my full space. I'm just going to say this is 2. So 0 to 2. Halfway in the middle of that is going to be 1. Halfway in the middle of this is going to be a half. And this would be 1.5 or 3 over 2. You could do these as decimals. I like fractions. They're nice. But scale it however it makes most sense to you. So that counts for our period of 2. We're going to go from 0 to 2. And amplitude. Now we need to scale our y-axis to account for this amplitude of a third. Doesn't really matter. I'm just going to say that this is 1 and this is negative 1. I'm going to try to split that into thirds. So 1/3, 2/3, 1. So this will be 1/3. This will be 2/3, and that'll be 1. I'll do the same thing down here. So negative 1/3, negative 2/3, negative 1. All right, so we're going to keep it pretty tight here. We're going to be between negative 1/3 and positive 1/3. We are doing a cosine graph. That's important. Remember, don't accidentally graph sine when you're trying to graph cosine. So cosine, if we're looking at our 5 friends, we start at maximum. I'll sketch a line here. We start at maximum, we end at maximum, minimum in the middle, and then the equilibrium points. So you can kind of think about it as making this sort of reverse V if you want, and then curving. Or I guess it's not a reverse V, it's a regular V. I don't know why I said reverse, but making a V shape. Obviously, we kind of smooth it out with a curve to actually sketch the graph in there, but the points themselves kind of make a V. But anyway, that's our 5 points that we're looking to graph. And let's put that on there. Yeah, there's no reflection to take into account. Remember, we're only going to 1/3 and negative 1/3. So let's do it. So our first point is at the beginning of our period, that's 0. And 1/3 at its maximum value. That's this one up here, first point. And we graph that 5th point, remember, all the way at the end, because that's where we also end. And then our 3rd point is down at the minimum, which would be right here, the middle, and down at the middle. And in the middles of those, at our quarter points and our 3/4 point, we are going to have midline points. And then it's about sketching the curve in. So let's go ahead and do that. This one is not oscillating very much. It's pretty compressed, just kind of bouncing back and forth there. And that is there. That is our cosine curve. All right, hope that was helpful. In the next video, part 3, we're going to be going over phase shifts, horizontal shifts, and also vertical shifts.